we're going to be looking at energy as an integral part of chemical reactions. And we're going to be including energy now in our balanced equations, something that we call a thermochemical equation. Okay, energy can't be created or destroyed, though, in a chemical process. That's the first law of thermodynamics, all right, which probably you've heard many, many times, right? But we're going to be obeying this law of thermodynamics, even if we're making a bunch of assumptions about obeying this when you do actual lab experiments, okay? But we can follow energy in a reaction. It can still be converted from one form to another without being lost. And in this case, we're going to see some chemical reactions will produce energy, right? And I think you'll experience this like the last time you went camping and built the campfire, right? That's a chemical reaction that gives off a lot of energy. You feel that energy as the heat that's produced, okay? There's other chemical reactions that absorb energy, like if you sprain your ankle and you want to use a cold pack, right? And you open up the cold pack and you shake it up and it gets cold. That's a chemical reaction. That chemical reaction absorbs energy. And so you feel that loss of energy by the fact that it took heat away from the surroundings and put it into the chemical reaction. So your cold pack feels colder. I can't talk this morning. Okay, so that's the concept. There's heat and there's temperature. The heat is the energy that's transferred. The temperature is how we measure that. Okay, but overall we have the energy, that's E here, of the universe. It's conserved completely. So we write this as in two parts. The energy of the universe is really divided into two things: the system, which is our reaction, this is what we care about, and the surroundings, which is everything else. Now, honestly, the surroundings, that's like the universe, the rest of the universe. But when we do experiments in the laboratory, we try to control that environment, and the surroundings will just be your reaction vessel that's housing the actual chemistry that you're doing. So this is actually looking at the energy. It turns out that following the energy as a quantity is very difficult to do, but what's very straightforward to do is measure the changes in the energy, especially between one equilibrium state and another. All right, so here I'm just going to say it's easy to measure the changes between equilibrium states. Now that's a fancy way of saying the starting condition and the ending condition. Okay, when you start the experiment and everything is stable and not changing, that's an equilibrium state. And then you do the experiment and then something changes. And when the experiment is done and everything's settled down, that's your final equilibrium state. And we can measure the change between them. We use this capital Greek delta for change. Okay, that's what that symbol means if you're not familiar with it. Now, if we're conserving energy, right, that means that they add up to being zero. We can then rearrange that and write an expression like this, where the change in energy of the system, again, that's our reaction, is equal to negative the change of the energy in the surroundings. Or I can write that in reverse. I can say that the change in energy of the surroundings is equal to the negative change of energy in the system, which is, bless you, which is our reaction. Now there's a negative sign here, and as you'll see in a moment, the negative sign is not negative energy. There's no such thing as negative energy. The sign, whether it's plus or minus, just tells you the direction of flow of energy between the system and the surroundings. So I'm going to write that on your slides in a little bit, okay? All right, now this idea about equilibrium states, okay, it has to do with what we call a state function. State functions are things that we can measure with this idea that we can't measure them directly, but we can measure them as they're changed. The change doesn't doesn't change. If we can measure something at equilibrium state 1, and we can measure that same quantity at equilibrium state 2, then that change will always be the same, regardless of how we got from state 1 to state 2. It's independent of the path that's taken between the states. And I like this mountain analogy that the textbook uses for it, right? If you're going up a mountain, there's imagine 2 ways you can make it up that mountain. But you start at the initial at the bottom and you end up in the final state at the top. You can take the little tram that goes up the mountain real fast, okay? Or you can take the winding path that switchbacks and sometimes goes down and then goes back up again, but you finally make it to the top. The change between the initial and the final is the same regardless of the path that you take. In this case, it could be altitude that we're measuring, or it could be the potential energy that's gained between the initial state and the final state, okay? Those are both what we call state functions. The value, the change is the same regardless of the way that you got there, or independence. So the delta is always the same. The change is always the same. Now we're going to look at that with respect to properties of chemical reactions. So in this chapter, we're focused on energy. And in particular, we're going to be looking at this kind of energy that we'll talk about in a moment, the enthalpy of a reaction, which is H. But there's other terms on here that you've probably heard of, like entropy, S, or free energy, G. You've also heard of pressure and temperature and volume. These are all state functions, just like altitude is in this mountain example, or potential energy is also a state function. In fact, when you have a capital letter that's italicized like this, I think that means it's a state function. I'm not positive on that, but I'm pretty sure that's true. All right, so this is an important idea that we're going to take in all of the thermochemistry experiments that we'll be exploring in this chapter. So I'll be coming back to this idea several times in the next couple of lectures. The units of energy that we're using, it's called the joule. It's a kilogram meter squared per second squared. It's also known as a Newton meter. And this is energy, okay? Units of energy. And it's a force. Newton is the units for force. It's a force times distance, for those of you who care, remember in your physics. Okay, so our focus is going to be, though, on the enthalpy, and I'll be defining that in more detail in a moment. But basically, the enthalpy of a chemical reaction, this is the thermal energy or heat energy at constant pressure. All right, so let's talk about heat and temperature in a little bit more detail. We use these words all the time, but what do they really mean? So heat, as a definition, okay, heat is the energy that's transferred from something that's hotter to something that's colder in temperature, okay? But it's energy. This is thermal energy. And again, this is something that we measure in joules. And when you have something that's hot, here's the red square, and something that's cold, there's the blue square. So here, let's say this one's cold. Here, I'll keep it in blue. Cold, and this one's hot. There's energy that's transferred between the two. So if I push them together and put them next to each other, you'll find that the energy is transferred from the material that's hotter to the material that's colder. Right? This is a transfer of thermal energy. Now, energy has the units of joules, all right? But when you measure this in the laboratory, you don't have a device that measures joules. What device do you use, do you imagine, that measures the thermal energy? What's it called? It's called a thermometer, right? Some call it a thermometer, but it's a thermometer, okay? So the thermometer, and the units in the thermometer is in degrees Celsius, yes? So we measure this, we measure the temperature with a thermometer. That's in degrees Celsius. So here we have the cold in degrees Celsius, we have the hot in degrees Celsius, but the transfer from hot to cold is the thermal energies being transferred until you get to the end of the experiment. What happens at the end of this experiment? Does the energy keep being transferred from the red block to the blue block, or does it stop? Does it switch so that now the one on the right becomes red and the one on the left is blue? Or does it stop? What happens? Who thinks it stops? Raise your hand. Who thinks that it transfers completely so that the one on the right is now red and the one on the left is blue? Good. It stops. But why does it stop? Ooh, equilibrium, I heard. That's the magic word. Yes. It's a thermal equilibrium. And at thermal equilibrium, the temperature of one is going to be equal to the temperature of the other. They've reached the same. If you think about the definition of heat, that it moves from something that's hot to something that's cold, then let's say it did go a little bit too far in the other direction, okay? And now we've made the one on the right a little hotter than the one on the left. That means the energy is going to be transferred from hot to cold. And if you overshoot it again, it's just going to keep going back and forth until it's completely equal on both sides. So in fact, things are at equilibrium, whether it's thermal or chemical or any kind of equilibrium, it's always going back and forth, okay? Even though when you're looking at it, if you measured both of them, it doesn't look like it's changing, but it's really changing back and forth all the time. So thermal equilibrium, that's what we get to at the very, very end. All right, so that's the connection between the temperature that you measure, how hot something is, but what is heat? All right, it's the transfer of thermal energy, and that's what we're going to be following in this chapter. All right, so when we're looking at the energy of our system, right, this is what we call the internal energy. So this is the energy of the system. So let's call this a chemical system. Sometimes you'll see this as just E with the subscript, int or internal. So what kind of energy do we have that's internal to our system? What is our system? They're compounds, they're molecules, or they're ionic compounds that we've been looking at a lot. We've been looking at how they bond. I've been talking about the bond energies, right? When we talked about single bonds and double bonds and triple bonds. They all have energies. There's vibrational energies, there's rotational energies. The molecule is spinning around. The bonds are stretching and contracting, or they're twisting. So there's small rotational, vibrational, and also stretching of bonds. So this is a stretching of bonds and molecules. But we also have molecules that are in motion, right? They're moving around. And hopefully from physics classes, or not even in physics classes, you may remember the energy of motion. That's kinetic energy. All of these can be thought of as kinetic energy. But we also have potential energy that's stored in those bonds. For example, we talked about like bond energies. When you have a single bond, it takes a certain amount of energy to break that bond. If you have a double bond, that's a stronger bond energy than a single bond. A triple bond is stronger than a double or a single, and it takes more and more energy to break those bonds. So we can think of that as potential energy. So that's stored in the bonds, bond energies. Okay. So all of these energies, we can think of them as thermal energy that we can measure by their temperature as we are undergoing a chemical reaction. And so we can break that internal energy into two parts. There's a heat portion that we're going to call Q, and there's a work portion that we're going to call W. And in this case, W, the work, it's pressure volume work. So when things are changing pressure or changing volume, that actually does work. It's a force, but we're not going to be looking at work. We're just going to be looking at the chemical energy, not the work energy. And with enthalpy, okay, we're going to be focusing on the chemical changes that involve the transfer of heat energy. So in other words, our focus is really going to be on Q, and the work part of it, the pressure volume part, we're basically ignoring that. Now, if you really want to know about pressure volume work and how that affects all this, you should go on and take physical chemistry later on in your education. But this is a foundational class. We're just going to be focusing in this chapter on the heat energy component. So as such, then we're going to be following, as I mentioned at the beginning, how that heat energy is really acting like either a reactant or a product in the same kinds of chemical reactions that we've been studying. So instead of writing a reaction that's just A plus B goes and forms C, all right, we're now going to be describing heat as another component here. So let's say C plus heat. Okay, and when we do that, we're going to be writing what's called a thermochemical equation rather than just a chemical equation. All right, so this is coming soon to a lecture near you. But we won't be getting into thermochemical equations until later in the week. All right, so let's talk a little bit more detail now about enthalpy, and I'll give you some definitions, and we'll explain them a little bit more detail. So the formal definitions for enthalpy are written at the top here. And formally, it's the internal energy that I just described, okay, of a system plus the product of the pressure and the volume. So enthalpy, and H is the letter that we're going to use for enthalpy. This is the internal energy plus the pressure volume work. And as I already mentioned, we're going to be ignoring the pressure volume work aspect of this. And under the conditions, under normal laboratory conditions or under regular biological conditions, right, those are always happening at constant pressure. And this is why, for the definition of enthalpy, it's always working at constant pressure. And for the experiments that we're going to be considering in this chapter, we're not even going to be changing the volume very significantly. Okay, so for our purposes and for enthalpy and how we use enthalpy, it's really just going to be describing the total heat content of a system at constant pressure. And so we can really describe it this way. Remember, Q is heat. So this is going to be heat at constant pressure. And H, this is a state function. So we can't really measure H directly, but we can measure the change in enthalpy from one state to another, from one equilibrium state to another. Change in enthalpy. So really, this is the definition for enthalpy that we're going to be working with in this chapter here, because we're not really considering the work part. So a couple of comments about these two terms, delta H and Q sub P. I'll probably just say Q, all right? But anytime we're using Q in this chapter, it's really Q at constant pressure. And you'll see that subscript P a lot. So now you know what it means. We're working at constant pressure. All right, so it looks like they're the same thing. And in many ways, they are the same thing. But a few differences in how we use Q and delta H in this chapter. So Q, that's the thermal energy or the heat energy of a reaction at constant pressure, okay? But that's going to be for the reaction that you're measuring. And you'll see what I mean by that in a moment, okay? The delta H is the change in heat or thermal energy per mole of a reaction. So the reaction that you're describing, the balanced equation, when you react a mole of material, or if you do a mole of that reaction, that's the delta H. So it's per mole of reaction, okay? And that's what the state function is. Because we're doing it by the defined reaction, that reaction, when it's at equilibrium state 1, like say when it starts, and at equilibrium state 2, when it finishes. Whereas Q, that's really the path that you take. Q is going to be the amount of material that you're actually reacting. You may not be reacting a whole mole of material. Maybe you're only measuring the reaction with 0.0125 moles, okay? That's going to be Q. That's going to be what you measure in that reaction. But then you put that in the context of how many moles were you reacting, that will tell you what delta H is. Okay, so they really are telling you the same things. It's just relative to what. And just to keep in mind that the units here are a little bit different. So here's the mathematical description of what I just described. Delta H is of the reaction, okay? This is per mole of the reaction, and this is measured in kilojoules per mole. Let's make that more clearly. Whereas Q, this is measured in joules. And the reason for that is just to keep the numbers more manageable, because usually you're not reacting a large number of moles, you're reacting a number of moles that's much, much less than 1. So Q will be measuring in joules, but when you convert that to delta H, when you divide it by the moles reacted, it gives you such a small number, or sorry, such a large number, rather, that we express it instead in kilojoules. And you'll see that for yourself when you do these experiments tomorrow in lab, and then also later in this week when we start working with some examples of this. All right, so that's the relationship between delta H and Q. You'll be using that a lot, so get familiar with it. Two more terms that I want to define for you. You've heard these before, but let's define them. They are exothermic and endothermic, and they have to do with the transfer of thermal energy, which is what we're talking about here. Now, this is always going to be relative to the system. How we define these. It's the flow of energy relative to the system, okay? If it's exothermic, that means the thermal energy is given off by the system. And so if it leaves the system, it has to go to the surroundings, and there's no loss of energy in that transfer. If it's endothermic, that means that the thermal energy is absorbed by the system, so it got that thermal energy from the surroundings. So the surroundings are going to get colder if it's endothermic. The surroundings get hotter if it's exothermic. Does that make sense? So the surroundings gets hotter. Should have put that in red, I guess. And here the surroundings gets colder. Now, you probably can't see it too well here. In this graphic from the textbook, you've got the system in the center, and then the surroundings is everything else. Remember, the system, that's our reaction. And you can see it when you get heat in, when the system absorbs energy, we're going to assign a positive value to Q. Q is greater than 0. When it's exothermic, Q is going to be greater than 0, which means that delta H is also going to be greater than 0, meaning that it's going to have a positive value. In an exothermic reaction, that's where heat is transferred from the system to the surroundings. So the heat goes out, we're going to assign a negative number for that, okay? Because, well, I'll tell you in a minute. So if it's exothermic, then Q is going to be less than 0, which also means that delta H is going to be less than 0. And the value of energy is going to be negative. Okay, so now I'm going to repeat what I said earlier, but I'm going to write it on the slide because it's that important, okay? It's not negative or positive energy. There's no such thing as negative energy. It's just energy. It's an absolute value of energy, okay? The positive and negative sign just tells you the flow of energy. That's our convention. If it's exothermic, it's all relative to the system, okay? If it's exothermic, that means energy is flowing from the system to the surroundings, and we give that a negative sign, right? So negative or positive is just the convention for the flow of thermal energy between the system and its surroundings. And again, the convention is relative to the system. So apart from that, you just have to remember which sign is relative to which direction, okay? Relative to the system. If the energy is leaving the system, so it's leaving it, it's negative. If it's coming into the system, it's positive. So as long as you can remember that it's relative to the system, you should be able to keep track of what's negative and what's positive. But it's all the same quantity. The absolute value of energy is what's important, and that's what's not being lost or gained when we move from state 1 to state 2. Okay, any questions on that? All right, so let's explore another property of materials now relative to heat, and that's called the specific heat or the specific heat capacity. Right, we use a C for that, and it's C sub P. So once again, the P, this is for constant pressure. And what specific heat capacity is, and sometimes we just call this specific heat, by the way. So if you ever say specific heat, you're really talking about specific heat capacity. This describes the energy, well, it describes the capacity for a substance to be able to absorb heat energy without it being affected, all right? But to put that in more simple terms, it's the energy required now it's specific, it's the energy required to change 1 gram of a material or a substance by 1 degree Celsius. And it's a reflection of how much energy does it take to get it to move, to get it to change in temperature. Well, the higher the specific heat capacity is, the more energy you need to supply to get it to change in temperature. That should make sense. Mathematically, let's look at the units of specific heat capacity. So I'm going to turn these words into units. It's the energy required, and energy is measured in joules. The energy required to change 1 gram of substance, so it's joules per gram by 1 degree Celsius. So it's joules per gram degrees Celsius. So let me write that a little bit more carefully. That's a multiplication dot here, and this is degrees Celsius. So it's joules per gram degrees Celsius. And you can see that up here on this table, although I don't know if you can see it on the slide, it may be too small, but those are the units, joules per gram degrees Celsius. And here is the specific heat capacity listed for all sorts of different materials, different metals, and you can look at those numbers, okay? And then look further down on this table. Here we have H2O in different states. Here's H2O that's solid, H2O that's liquid, H2O that's gas. Sorry, folks, but it's only water when it's liquid. That's a problem with the little typo in the textbook, right? It's ice or it's vapors, but anyway, you get the idea. Take a look at those values there. Let's look at water in the liquid state, because that's where you're going to be using a lot in this chapter. 4.18 joules of energy is what it takes to get 1 gram of water to change by 1 degree Celsius. And compare that with how much energy it takes to, say, move 1 gram of aluminum or 1 gram of carbon or 1 gram of gold. It doesn't take much energy to get gold, or look at iron, 0.45. Let's stay with aluminum for a moment, okay? Let's say I want to boil some water at home, okay? And I have an aluminum pot, and I put some water in it, okay? Look at the differences between the amount of energy it takes to get water to change by 1 degree Celsius versus the amount of energy it takes for aluminum, okay? The aluminum is going to get hotter a lot more quickly than the water will, right? Based on these numbers. I think you all have practical experience on this. If you start boiling that water, okay, you can stick your hand in it. I think I demonstrate this in the lab video. It's kind of funny. But you can stick your hand in it. It's not that hot, the water, right? But you know, the stove, it's on high, right? You don't want to do this, you know, you don't want to wait too long to try this experiment, right? But and don't try it, please. But I think you'll all agree that you can put your hand in the water and it won't hurt, but you probably don't want to be touching the pot, the aluminum pot that it's in, right? Because that's probably a lot hotter than the water is. You think? You had a question? So yeah, so the question has to do with, do these numbers also have to do with the heat dissipating from it? And the answer is yes. The transfer goes both ways. That's why, you know, I'm talking about heating things up, but if it cools down, the same principle happens as well, okay? You can use these numbers to figure out, well, how much energy is going to be given off by the water as it lowers in temperature, right? We'll be able to do both of those things. But keep in mind now that when we follow the energy flow, is it going into the water or out of the water? Is it going into the system or out of the system? The magnitude of that energy change is dictated by the specific heat capacity, but the sign that we put on it, positive or negative, okay, that's going to change. Okay, so that's specific heat capacity. Now you'll also notice on the right-hand side here, we have another set of values. This is joules per mole degrees Celsius. This is what we call the molar heat capacity. It's the same thing. This is per gram. And this is going to be per mole. So the units are similar, except now instead of per 1 gram, it's going to be per 1 mole. The amount of energy it takes to take 1 mole of material and change it by 1 degree Celsius. And notice here I'm saying to change it. I'm not saying whether it gets higher or lower. To change it in either direction, okay? Energy in, energy out. Now, I try to keep all my examples using specific heat, so per gram, right? But the textbook likes to use per mole in a lot of its examples. So just make sure that you keep that in mind. But if you look at these numbers, they should only be differ by the molar mass of, in this case, H2O, right? And you know what that is? It's 18.015 grams per mole. So if this is per gram, right? And this is per moles, and you know what that difference is, right? 18.015 grams per mole. That should be the difference between these two columns. Well, for water, okay? It just differs by the molar mass. So it's easy to convert from one to the other if you have to. In these examples, then, we're going to be, all of these energy changes are dictated by the specific heat capacity of the material that we're using. So once again, here's the specific heat capacity, C sub P. And for water, right, that's 4.184 joules per gram degree Celsius. We'll be looking at that in a moment, okay? But the units of this, once again, this is joules per gram degree Celsius. This is what dictates the transfer of energy, how much. And then you're going to be using a thermometer to measure the change in temperature. That will tell you how much energy was transferred, okay? So we're going to multiply this by whatever that change in temperature was, delta T. And that's going to be in degrees Celsius. And we're going to be doing this on a specific mass because this is per gram. So how much material are we measuring? That's the mass. M. The mass is in grams. So notice how the units here cancel out. Grams cancels with grams, degrees Celsius with degrees Celsius, and that leaves us with joules as a unit, and that is, of course, the units of thermal energy. So Q that we measure is equal to the mass times the specific heat capacity times whatever that change in temperature was. And by convention, all of these deltas, so delta, I should have said this earlier, delta by convention is always going to be final minus initial. Okay. So anytime we have a delta something, in this case, delta T, it's the final temperature minus the initial temperature. If it's delta H, it's the final minus the initial, and so on and so forth. All right, so let's take a look at this question now. How much energy is required to raise 50 grams of H2O liquid by 5 degrees Celsius? Well, this should be pretty straightforward, but I need to tell you that the specific heat capacity of water is 4.184 joules per gram degrees Celsius. And you'll always be told this, and that, you know, if you need it in a problem, you'll be given that value, or you'll have a table where you can look it up. So now let's just plug everything in. All right. So the Q, the heat related to, or the heat necessary in this case, because we're raising it, so we need to put heat into the system. So is Q going to be a positive value or a negative value? Heat's going into the system. Positive, all right? And you'll see that in the temperature change, okay? But let's just put this in. So Q is equal to the mass of the water, that's 50.0 grams, multiplied by the specific heat capacity, 4.184 joules per gram degrees Celsius, and we're raising it by 5 degrees Celsius. So you can put in whatever temperatures you want. Let's say it started at 25 degrees and it ended then at 30 degrees, right? Or you can make up any one you want, because again, temperature is a state function. All we're doing is raising it by 5 degrees. But we can say that the T initial, let's say it's 25 degrees, T final is 30 degrees, delta T is final minus initial, 30 minus 25. So it's positive 5 degrees Celsius. That's what's going to give us our positive value for Q. If we did the reverse calculation, if we were lower, if the question were asking us to lower it by 5 degrees, then T final and T initial are swapped, and now delta T is a negative number. That gives you a negative value for Q. Okay, that's where the sign convention comes from. But remember, it's not positive and negative energy. It's just whether the energy is flowing into the water or out of the water. Okay, so if you do a calculation on this, and I get 1,046 joules, it's a positive number. Okay, if I want to express that in kilojoules, I could, because if let's see what the delta H of this is. This is Q, all right? If I want to know what delta H is of this reaction, well, I need to know how many moles of material were contained in that 50 grams of H2O. So let's do that. We had 50 grams of H2O. The molar mass of H2O is 18.015 grams per mole. 50 divided by 18.015 gives us 2.78 moles of H2O. So we want to express delta H in kilojoules per mole, not joules per mole. Okay, so let's put this in kilojoules. That would be 1.046 kilojoules. And so delta H of this reaction, and in this case, the reaction is raising H2O by 5 degrees. That's the reaction. Okay, the delta H of this reaction, it's going to be Q of the reaction divided by the moles that were reacted. In this case, it's going to be 1.046 kilojoules, per 2.78 moles. And that gives us 0.376 kilojoules per mole. Okay, this is a relationship that you're going to be using a lot in this chapter. Q is equal to M times the specific heat capacity times delta T. You'll be using it a lot in lab tomorrow. Tomorrow's lab is on calorimetry. And a calorimeter is something that is very, very useful for us to be able to actually measure what this heat transfer is, because we're measuring it with a thermometer. Okay, so here's your definition of a calorimeter. And it's making use of this relationship between whatever the heat transfer that we can measure in the calorimeter, whatever happens in the calorimeter, the opposite must have been happening in the reaction. So I'm going to write this relationship here. The reaction is what's happening in the calorimeter, because really what we have here, this is our system, the reactions of the system, and the calorimeter is going to be the surroundings. It's everything else. And you remember, hopefully from the beginning of our discussion, that you can transfer the energy between the systems and the surrounding, but you're not losing any energy in that transfer process. Okay, so in the calorimeter, this is now our universe. And we're going to assume that no energy escapes the calorimeter. It's all going to stay in the calorimeter. And we're going to use what's called a coffee cup calorimeter, because that's exactly what it is. It's a styrofoam cup, or I guess a foam cup we call it. Okay, and we're going to assume that that's perfectly insulated. And in that cup, we're going to have some water. Here's your 50 grams of water. Okay, and you've got a thermometer in there. Okay, and this is it's insulated, so we're assuming that no heat escapes it. And you've got, here's your water in here, so, and you're going to have some reaction in there, and you're going to be doing several different kinds of reactions. You're going to be dissolving some material in the water, and you're going to measure whether heat is given off or taken up by the calorimeter when you dissolve a substance. You'll be mixing two aqueous solutions together, One has an acid and one has a base, right? We looked at that acid-base reaction in last chapter, that neutralization reaction. There's a heat component related to all chemical reactions. And so when you mix the acid in aqueous solution with the base in aqueous solution, you'll be doing that in the calorimeter. And the temperature that you measure on the thermometer will tell you what the energy transfer is. You'll be able to actually calculate the enthalpy of that reaction. But it's all done in the context of this coffee cup calorimeter. So what we're measuring then is the water in the calorimeter. We're measuring Q cal. That's going to be equal to the mass of the water and the specific heat capacity of water and you're going to measure what the delta T of the calorimeter is. Okay, so that's mass of water, this is specific heat capacity of water, and this is your delta T. So if the reaction is exothermic, that means that the system, the reaction is giving heat off to the surroundings, right? If it's exothermic, the reaction gives off heat to the surroundings, to the water. So the Q of the calorimeter is going to be what? Positive or negative? It's going to be positive, which means what happened in the reaction? That means Q of the reaction is negative, meaning that the reaction is exothermic, okay? But you're going to have to be playing around with the signs. If the reaction is endothermic, that means heat is absorbed from the water. So the Q of the calorimeter that you calculate, that's going to be negative, right? It's absorbed from the water. Let me be specific about this. When the heat is given to the water, that means T final is greater than T initial. So TF minus TI is greater than 0. If heat's absorbed from the water, that means T final is less than T initial. So T final minus T initial is going to be less than 0. Right? It's a negative number, which means that Q of the reaction must be positive. Okay? So you're going to have some chance to practice playing around with the names, how you define things, following the energy of these reactions, and using the positive and negative signs, calculating things in the right way with final minus initial. And you'll start practicing with all this stuff. Okay?